Okay, so let's see see how we can do that. And that will lead us to like nonlinear SVM, and that's also called support vector machine. So what will happen is we will still learn like your linear boundary. Okay, it's not that we're trying to learn nonlinear boundary, but still like this is the trick. It will work as it is actually nonlinear. Okay, so I think this is a pretty cool idea. Bear with me, and we can come back to this again if you don't understand this. Now look at this Euclidean space here. So these are all the samples coming from red class and blue class, and you can clearly see that whatever linear boundary you try to draw, you cannot separate these two classes. But you can have a non-linear boundary. Let's say this circle, and this circle can actually very easily differentiate between blue and red. Okay, now what you can do is you can project all of these points. So right now they are in two-dimensional space. What you can do is you can try to project them into three-dimensional space. Okay, and how we can do that, I mean, you can use any function to actually project this to three-dimensional space, and I will give you like one example how you can do it. So this is your dimensionality of the source domain. So in this case, two-dimensional. What you do is you come up with a function which is actually going to project each of these points to a high dimensional space. So in this case, we can go from two-dimensional to three-dimensional. And let's say it looks like something like this. And one simple function for the psi for this particular case could be, let's say, a square function. So let's say you just square the x and y values. So what will happen? These are like bigger values, okay, in terms of like, so all the points which are outside the circle, they will have bigger magnitude, right? It doesn't matter whether it's in the x direction or in the y direction. And even if it's like on this side, if you just look at the magnitude, it's going to be bigger. It will have a negative sign, but still it will be bigger. And that's the reason they will be like lying outside the circle. Okay, so for example, let's take an assumption. This is the origin 0 cross 0. And let's say this point is 1 cross 0. This is 0 cross 1. Again, it will be negative 1 and 0. And this will be, let's say, 0 and negative 1. Okay, so all the points inside the circle, wherever they are, it doesn't matter. The values will be between 0 and 1 for both x and y dimensions. And similarly, all the points which are outside the circle will have values greater than 1. Mostly, this is like a corner case, just ignore this. But more or less, they will have values greater than 1, both for x and y. Now, if this function is, let's say, square function, now what will happen is all these negative values will become positive because you're taking a square. And if the values are bigger, then the square will also be bigger. Okay. So that way you are actually projecting this into three-dimensional space. So you add one more dimension here, let's say z. And then you can see that all these points are actually going away from the center. So this was their origin, and all they are like just flying away. They will move away, right? You can just get like xy values for those. And similarly, all the red points, again, you will square, they will become positive, but still they will remain small. They won't be as big as blue. Now, once you have done that, then what you can do is you can actually come up with a linear plane which can separate the red dots from the blue dots. Okay, so this is also called like a kernel trick, and the idea is to just learn this kernel function which can project your points from small, like a very low dimensional space to a high dimensional space. And it is interesting because what it's trying to do is it's trying to project in high dimensional space, but also making them linearly separable. All right, so that's called support vector machine. And so that was a kernel trick which we just discussed. And again, you can learn like all of those, lot of kernels in your support vector machines. We are not going to go into detail because I think just that part was really interesting how you actually do that. So in this case, you can actually learn these nonlinear boundaries. That's one example. Okay, so in this case, you're trying to learn two different nonlinear values. That will do the trick. But again, if you project that like to a high dimensional space, you can just learn like one kernel, and you don't need these two different classifiers. Okay.